Hi, everyone. I'm Travis, and I've been at the CCEM for over 10 years. Most of that time has been spent doing focused ion beam and electron microscopy work. But 1 year ago, we installed a new FIB with a femtosecond micromachining laser. This has dramatically expanded the maximum size range of FIB-like tasks and enables us to do many new and exciting things. So I'll tell you all about it. This presentation isn't about FIB details. We've covered those in previously webinars that we have uploaded. You can find them on the CCEM website or our YouTube channel. If you need to watch this one again, it will eventually live there alongside the rest of the webinars in our series. So today I'm mostly focusing on what is new here, which is the laser, but FIB still plays a major role because it's a combination of the femtosecond laser abilities with FIB-SEM methods that really drives the applications that we're most interested in here in the world of microscopy and characterization of materials. So lasers are certainly not new, and I'm not going to delve deep into laser photonics here, but a brief history is that Zeiss introduced a short pulsed laser add-on to their FIB platform in 2012. And it had some practical applications, but the ablation mechanism of the nanosecond laser was a thermal effect that caused localized melting. So that heat affected zone was quite large compared to the typical length scales that microscopists want to characterize. It would have been time consuming to remove the thick damage layers so that the implementation wasn't widely adopted. Femtosecond lasers, though, have already been around for a while, but perhaps not quite ready for commercialization, partly due to cost. There was some developmental efforts on an FEI platform that I found published in 2012, but an implementation on a Zeiss FIB was published in the PhD work of Manuel Pfeifenberger in 2017 that closely resembles the laser FIB of today, which partly led to the announcement of a commercial version by Zeiss in 2020. Thermo Scientific also announced their commercial implementation, which they call a tri-beam, I think in 2020, but don't quote me on that, I'm not certain. So more about exactly what a femtosecond laser is. Well, rather than a continuously emitting laser, a pulsed laser produces highly energetic but short-lived repeating pulses with large time gaps in between. Nanosecond lasers are generally considered short pulses, but ultrasecond lasers are generally below around 100 picoamps. Sorry, seconds, picoseconds. I'll remind you that a femtosecond is what comes after pico. So the duration that the laser pulse is delivering, the energy is within the femtosecond time scale. The gap between pulses is the period, which is more commonly described by its inverse, the pulse repetition rate or pulse frequency. This gap between laser pulses is relatively huge. It's about 10 million times the pulse duration. You might be wondering why so much downtime, but consider how much energy is being delivered in each pulse. On our system, the maximum energy per pulse is 10 microjoules, but this is delivered in just 350 femtoseconds. So in that brief moment, the power corresponds to about 29 megawatts. That rate of energy powers about 36,000 homes. Of course, that power can't be sustained for long. The average power delivered is closer to 10 watts, which is more like an LED light bulb, except that it's delivered to a spot about 15 micron diameter, which is 56 gigawatts per square meter. And that's about 56 million times the solar irradiance at sea level. So even a continuous wave laser produces a lot of local heating. Now remember, we don't want a heat affected zone. Here's why we want to cram all that energy into as short a time as possible. It changes the ablation mechanism. Now the physics is complicated, so this is going to be a huge oversimplification, but with continuous lasers and even nanosecond pulse lasers, the ablation mechanism is mostly thermal. So Heat transferring to the material is responsible for ablation, and some of that heat is dissipated to the surrounding material, causing a large heat affected zone. With ultra short pulses, the energy is delivered so fast that the atoms vaporize before there is enough time for heat transfer to the surrounding material to occur. Basically, the ablated material takes the energy with it, so there's not much heating of the neighboring material, and so the ablation process is said to be non-thermal. But that doesn't mean there's no heat transfer. We have to acknowledge that the beam profile is a Gaussian shape. At this point, I should define an important parameter called laser fluence. This is the energy density, or the energy that's delivered to a unit area of the material, and it should consider the beam shape. So that complicates things a little because there are a few different standard definitions of beam diameter, and also a beam may not even be perfectly Gaussian. So quantifying the laser fluence is actually a bit tricky. For a material, there is a minimum energy density required to cause ablation, and this is called the ablation threshold fluence. It has also been discovered that as the laser fluence increases above the material's ablation threshold, the ablation rate begins to increase dramatically, and this point is called the transition fluence. In the graph here, it's the kink where the lines shoot upward. In this high ablation regime, a thin molten layer will form on the lasered surfaces, as well as other crystallographic damage effects like dislocations, phase changes, and even amorphization. Since the beam is a Gaussian shape and ablation only occurs above the threshold fluence, the outer part of the beam doesn't deliver the same peak energy as the center. That beam tail, which is below the ablation threshold, transfers all of that energy to the surrounding material. So there still is a small heat affected zone in femtosecond laser ablation, even though the ablation mechanism is itself non-thermal. Some of that energy is left behind. This is why large time gaps between the laser pulses are beneficial. Putting it simply, this gives the material time to calm down so that the excess energy remaining in the sample doesn't accumulate too much to cause microstructural changes. Size of the heat affected zone and extent of structural damage is, of course, highly material dependent, and there is also a wide variation in both the ablation threshold fluence needed for different materials as well as the transition fluence. So the choice of laser parameters can minimize the heat affected zone. Ideally, we'll want to keep the fluence between the ablation threshold and the transition point, or at least don't greatly exceed it, which means carefully choosing the laser power and repetition rate. The heat can also be more gently spread across the sample by increasing the beam velocity so that the pulses are spatially farther apart. The incident angle of the beam to the surface also affects the fluence. Here's what I mean by that. A glancing angle beam effectively reduces the fluence by spreading the spot over a larger area compared to when the beam hits a perpendicular surface. This typically means we can get smoother cross-section faces compared to the rough bottom in a trench. So what is a typical heat affected zone with a femtosecond laser? First, I'll show you some comparisons to a nanosecond laser. So here, it's a 100 micron thick steel foil with 180 micron diameter hole blasted through it. The nanosecond laser hole shows an excessive amount of splatter and resolidified materials, a wide debris footprint, and poorly defined edges. The femtosecond laser on the right shows minimal debris, a fairly sharp edge, and a decently vertical sidewall angle. Here's another example. This is a 500 micron long cantilever fabricated in a 25 micron thick tungsten foil. The smaller images are showing a zoom of the top surface, the sidewall, and an EBSD pattern acquired from a fib polished cross-section of the edge. Normal rolled tungsten foil should naturally have very thin and elongated grains and a high defect density. The nanosecond laser produces a debris-covered top with rough and melted-looking sidewalls. The EBSD data shows a few microns of large recrystallized grains, and further inward, the elongated grains have coarsened. The femtosecond laser produces a debris-covered top with rough and melted-looking, femtosecond cantilever has relatively planar surfaces, and check out the EBSD data. That is how elongated rolled tungsten grains should look like. Basically narrow all the way to the edge with no visible coarsening or laser-induced damage. For many materials, femtosecond laser heat affected zone is insignificant. I've seen papers showing measurements of just a few nanometers for this, but in some materials there are heat effects a few hundred nanometers inward, and rare cases perhaps closer to 1 micron. Most of the time it's a non-issue, and there are more significant effects to worry about with laser processing, which I'll get to soon. One of the most notable artifacts on laser surfaces is a ripple texture that has become commonly known as laser-induced periodic surface structures, or LIPS. These ripples are caused by wave interference effects. They typically have a spacing of a few hundred nanometers, and their amplitude is roughly on the same scale, about 100 nanometers. The LIPS can make it difficult to see the sample microstructure and are unavoidable, but they are affected by laser parameters and can therefore be reduced to the point where the microstructure is visible. However, optimizing for LIPS minimization can have unintended consequences to the other quality metrics, such as the slope of the trench walls, for example. If necessary, a FIB cleanup can remove them. However, since lasered cross-sections are intentionally huge, that could add potentially a few hours if you really need dimensions in the hundreds of microns to be cleared. Next, coming back to the idea of combining a laser with a FIB, the switch to femtosecond laser over nanosecond has greatly pushed the quality of results far enough to enable electron microscopy and materials characterization techniques on laser ablated samples. This technology has evolved, and costs have lowered enough for this to be a feasible add-on. So what does it do? Well, the laser can blast away material very quickly, up to a few million cubic microns per second. And that's roughly 1,000 times the highest plasma FIB milling rates and about 30,000 times the highest gallium FIB milling rates. Although that's not totally fair, since we won't always be using maximum laser power and repetition rates, or perhaps it's more like 500 times PFIB speed, which is still amazing. So this enables efficient access to a previously untapped length scale with FIB-like methods. I have to add a disclaimer here. These length scales that I'm showing, the ranges are just my rough approximations where I would suggest these beams are optimally utilized. I know gallium FIB can definitely cut far more than 30 microns, and PFIB can do sub-micron things and make TEM samples. I've done all of this myself many times. But if you have the freedom to choose, and we do here at CCEM because we have all 4 of these systems, this is roughly how I distribute tasks based on size. So in terms of FIB-like methods, the femtosecond laser takes a big chunk out of the PFIB's territory, removing materials in the hundreds of micron scale many times faster, and then pushing far beyond that into the scale of a few millimeters. Still fast and feasible. Now finally, I'll introduce our Zeiss Crossbeam 350 laser FIB. This is of course a full regular FIB-SEM plus a femtosecond laser, which is made by an international laser technology company called TRUMPF. The laser is mounted on top of the airlock and does the laser processing inside it in a decent vacuum. It's a green laser at 515 nanometer wavelength, 350 femtosecond pulse duration, up to 10 microjoules delivered by each pulse. And we can vary this energy by adjusting a power percentage from 2 to 100%. Spot size is about 15 micron diameter, and unlike FIB, this does not vary with energy or dose, so it's a bit strange. We can vary the frequency or repetition rate from 100 hertz to 1 megahertz. The Rayleigh length is 150 microns, which is the distance from the focus spot to where the spot size is doubled. And a common definition of the depth of focus is double the Rayleigh length. So this laser beam is decently focused for about 300 microns. And that's fine because we can set and track the focus anywhere within a 6 millimeter depth range. and scan that over 40 by 40 millimeter area on our laser holder. Also, the maximum fluence, as I said before, is a bit tricky to calculate because the spot size isn't precisely defined, but my calculation estimate is that it's about 11 joules per centimeter squared. The system was installed in April 2022, just about a year. And so it's still among the early adopters we are of LaserFib. Plus, we were the first installation with burst mode, but more on that later. The primary operator is me, although I do sometimes use 4 other electron microscopes here. This FIB is also equipped with a Leica cryosystem, and we have Atlas V, which is a hardware and software package with an additional microscope control user interface, automated FIB tomography acquisition, automated 2D mosaic acquisition, and a workspace to facilitate correlative microscopy, which I will discuss later. To show you the laser workflow, I'm not going to reinvent the wheel. Here's a video from Zeiss. I'll talk through it. So first we load the sample into the airlock, pump it, then transfer it under vacuum to the chamber. Sample holder for laser work has 4 fiducial apertures that we use to enable the laser to localize our targets. In this example, the sample has buried treasure deep inside that we need to access, and this location is informed by X-ray microscopy. More on this later. We save an SEM image of the surface at target location, export it to the laser mill program along with the stage coordinates, then we locate the fiducial apertures, also importing their stage coordinates to laser mill. Now we target the location. Now the target location is linked on the holder to the aperture positions, which is independent of the stage. We return the holder to the airlock and then scan the apertures with the laser. Now the laser knows how to find our targets. Yada, yada, yada. Then the laser blasts away at the sample to reveal an internal cross-section. And follows this up with a finer polishing step. Then we transfer the holder back to the SEM. Three millimeters, so big. Next, we tilt the stage and acquire a cross-section image. 1.6 millimeters deep, and the features are quite visible. But here we still follow with a FIB polish at the target location. And that's actually assisted by the slope of that cross-section. Now we bask in the magnificence of our efforts. Crossbeam. Okay, I'm going to fill in some details. You may be wondering why the laser is in the airlock and not inside the SEM. I'll show you. There's a camera in the airlock so we can watch the laser in action. Here I was cutting through a silicon carbide wafer. You usually see the glow at the impact area, but sometimes you can see how hot debris sparks fly all over the place like we do here. Laser ablation is filthy. This debris gets everywhere on the sample, on the holder, on the walls of the chamber, and on the protective glass above this area. So I'm quite happy that this process has been isolated from the ultra clean microscope chamber and is in the airlock. As I said before, the laser scan field is 40 millimeter by 40 millimeter, but we can't cover the fiducial apertures, so it's effectively a little less. For a diagonal square, that means 36 by 36. And with the corners outside of the scan field. For longer and narrower rectangle, such as a glass slide, could be about 75 millimeters long to fit through the gate valve and about 20 millimeters wide, although there's room to overlap the aperture discs a little. And for a circle above the aperture discs, we can fit 36 millimeter in diameter or 31 if we're between the apertures. For the sample height, remember we have a 6 millimeter focus range, but the bottom of that begins a little bit into the standard SEM stub surface level, so that actually only leaves us with 4.8 millimeters remaining for the sample. But I have a workaround. With a low profile stub, the sample height can range from 0.4 to 6.4 millimeters. Or if we just copper tape the sample right onto the holder, then we've got a 2 millimeter to 8 millimeter range. And same if we mount the sample to the side of a stub, starting from the bottom. There is one more option. We don't currently have this, but Zeiss has developed a new low profile holder where the sample sits well below the holder surface, which enables a height range of about 5.8 millimeters to 12 millimeters and is a 32.8 millimeter diameter, which holds standard metallographic mounts. So that's really good. As promised, I'll tell you about burst mode. Here's how it works. We can use 2, 3, 4, or 8 bursts. In burst mode, the maximum frequency is divided by the burst number to limit us to the maximum, to limit us to, to limit us to a smaller maximum average power, which is about 10 watts. What's different here with burst mode is that the pulses will now hit the sample in tight sets where each pulse is only 20 nanoseconds apart. We have a bit of freedom to fine-tune the spacing between the burst pulses in 20 nanosecond increments. So for example, this 2-burst pattern has 3 20 nanosecond gaps between each pulse. So it's a 60 nanosecond gap. And then each set can be as close as half the maximum frequency allows. Now the big question is, how does it affect the sample? Well, as far as I can tell, right now there's only very limited information available about the effects of burst mode, but there are a few generally accepted conclusions, and I have my own experiences to support these points. Part of the difficulty is that lasers with different specs produce different results. And there are many different femtosecond lasers out there in the world today. So at this fine level of optimization, it almost doesn't even matter what the parameters someone else finds as ideal are for their different laser system. Generally though, I think it's safe to say the ablation rate is significantly higher with burst mode, at least typically, and this seems to make the biggest difference with semiconductors and insulators. But the burst condition that maximizes the ablation rate is not usually going to be the same that maximizes surface quality or the other positive metrics of quality. But that doesn't mean ablation rate and quality are directly inverse either. I think it's also generally known that burst mode can improve the taper angle, meaning steeper sidewalls. There are other important affected qualities such as surface smoothness and the magnitude of the lips, the accumulation of debris is another, and heat effects that could be positive or negative depending on the choice of burst parameters and varying widely with different materials. So for someone like me who has to work with all kinds of materials, that's a lot of optimization. There's no one best universal burst mode setting, especially considering that even with the same laser and same material, the existence of trade-offs means that what's best for one project is not always best for another. However, burst mode is still worth the effort because any mid-range, non-extreme setting is usually a big improvement over not using burst mode at all. Maybe a thorough optimization isn't practical, but a good enough, that could go a long way. I haven't explained why burst mode helps yet. Much of that is deeper into physics than I want to go here. Okay, fine. While metals absorb the laser photon energy directly to the conduction band electrons, some of the atoms, especially at the beam tails, may not have been excited above the ablation threshold. So a second pulse could push those atoms above the ablation threshold, effectively increasing the ablation rate. For semiconducting and insulators, the electrons first need to be excited above the band gap, and one photon may not have enough energy to do that. This green laser light is a 2.4 electron volts photon, and many materials have a larger band gap and will therefore be transparent to it. However, laser light absorption can still occur due to so-called non-linear optical processes such as multiphoton and avalanche ionization. Due to these phenomena, ultra-short pulses can still ablate transparent material. While one pulse contains far more, one laser pulse contains far more than just one photon. Some of the atoms may have only interacted with one photon though, especially around the beam tail where there aren't that many photons, or at least not enough to reach the ablation threshold. So additional burst pulses can boost an already energized area to exceed the ablation threshold via a multi-photon interaction and effectively increase the ablation rate. These effects require subsequent pulses to land before the effects of the previous pulse fully dissipates, which is why the burst mode pulses must be close. But if there are too many pulses too close, well, that could potentially push the material far above the high ablation rate regime and lead to poor quality and thermal effects. This could also explain why the most extreme burst mode conditions usually aren't the best performing ones. And when a high burst mode crams too much ablation together, a shielding effect from ejected material and plasma formation can reduce the ablation efficiency too. Here are some preliminary examples from Zeiss showing some of the benefits of burst mode. I don't know what parameters they used here, but they plan to put out a white paper on this topic soon. Anyway, this is consistent with my experiences too. Definitely steeper sidewalls and sometimes smoother cross sections and maybe a reduction in the size of lips. Backing up a little to the laser fib workflow, there was a significant step in that video that was totally skipped. Setting up the laser processes and parameters. This is often the most time-consuming part of doing laser fib actually, since the holder transferring is fast and the laser ablation is usually fast. So here's a view of the LaserCAD software. We import one or more SEM images that we saved during fiducial registration, and that location of the SEM image is precisely mapped to the actual location on the holder in the airlock for the laser to target. This step is also how we establish the right focus to use for our laser, because when the image is imported into this program, we receive the focus offset number, which is based on the focus difference in the SEM image between that and the fiducial apertures during the registration process. So with this CAD, we can produce nearly any kind of shape. In this case, below the SEM image is a cross-section trench cut for site preparation of a large volume fib tomography acquisition. I have a rough trench followed by a medium trench and then a fine trench. So I just need to line up my shapes with the feature in the SEM image. In this case, that's the edge of the sample, and then I can click activate on the laser process. Now here's another example. This is a more intricate design. Precise dimensions were needed here, so I had to use many different circles and rectangles to set that up. But then I can delete the lines that I don't want, then fill in the parts to be lasered, and build an array with that shape. So then we get what I have in the bottom right. You'll see what this one does, though, later on in the presentation. With so much sample movement from the SEM registration into the airlock, it's fair to question the accuracy of laser positioning relative to the target location. I've done a minor amount of testing things and also a bit of recalibrating the global positioning offset to optimize for the center of the holder. This isn't a thorough analysis, but I have some anecdotes on accuracy. It's pretty good. Near the center of the laser holder, I typically get about plus or minus 2 microns from my target. This gets worse the farther away we go from the center, so when high accuracy is needed, it's best to try to place the sample target near the center of the holder. Within a diameter of about half the scan field, the error is probably about plus or minus 5 microns. The outer portion of the scan field is more like plus or minus 10 microns, but sometimes a little worse. However, the error is usually a similar magnitude and direction each time you try it in a localized area. So that's quite repeatable, which means it's correctable. Here's how to do that. So you can do an accuracy test near your target location, then you measure the difference between the target and the actual laser position after doing that. Then you apply a local offset based on the measurement into the laser mill program to correct for the X and Y error. With that established, the localized accuracy can get to about plus or minus 2 microns. Although performing this procedure is often a bit more time consuming than just dealing with the consequences of having a bit less accuracy. Oh, and sometimes the sample itself moves during ablation, like if it's a flimsy thin foil or it's not well secured to the stub. And this can cause big positional errors, but that is somewhat preventable. So laser ablation, as I said before, is quite filthy. Trying to manage the effects of the ablation debris on the quality of the laser cuts has been pretty frustrating, and I think this is the biggest problem in laser fib operation right now. There is a system built into the airlock for managing debris called the CrossJet, and it helps a lot in one way, but it causes headaches in another. Here's why it's necessary. There's a protective glass disc above the sample which protects the laser optics from debris. When ablating large volumes of material, the protective glass gets thoroughly coated with debris and it can easily get to the point where it blocks most of the laser light from transmitting. This can happen in the middle of long laser processes, and that prevents ablation from continuing, so really the glass must be cleaned. But most of the time it comes clean without too much effort, but not always. Sometimes it takes a bit of scrubbing. So the CrossJet system that flows a stream of nitrogen gas across the bottom of the protective glass. This keeps the glass quite clean by collecting flying debris and carrying it away to our airlock exhaust line. With the CrossJet, we can continue laser ablating literally for hours continuously. This sounds great until you look at the sample and see all the extra debris that accumulates. For cross sections, like my example there, you can have many microns of debris piling up at the edge in a very rough way, and that causes the laser to produce very uneven cross-section edges, much like curtaining artifacts that you may know from fib. You can see from my comparisons, first I did a cross-section with the CrossJet on, and then the same laser process with the CrossJet off. The difference is shocking. Even after cleaning off the debris, the cross-section quality with the CrossJet on is still going to be far worse. But here's why it's often necessary to use. Without the CrossJet, after about 30 million cubic microns of material removed, the ablation rate slowly declines, maybe not so slowly. And after about 60 million cubic microns removed, the ablation basically stops. This can happen after just a few minutes of ablation. However, when the CrossJet is active, the ablation rate is constant and reliable. So it's a painful trade-off here, but many laser applications, it's essential to activate the CrossJet. You just need to ablate large volumes, which you can't do without it. At least I've figured out a few strategies to help a little bit. For small laser processes, just don't use the CrossJet and submit to cleaning the glass each time. You can also use a lower laser fluence to mitigate debris accumulation somewhat, but that also slows the laser processing. Yeah, but sometimes it's worth spending the extra time to go slow if that quality is really good. High volume rough cuts should be done with the CrossJet for sure. And it can be turned off though for the fine cuts, but the fine cuts work best if the debris has first been cleaned off the cross section and the edges. So doing a physical cleaning step means that the sample needs to be re-registered to maintain positional accuracy, and that adds more time to the process. Also, it's a bit difficult to remove all the debris. Some of it seems to be fused or melted onto the surface, especially at the edges of where the laser process has worked. And that's the worst place for debris to be. So I've been trying a variety of tactics to remove the ablation debris, and here's my current opinion on some of them. Vacuuming and rinsing only goes so far, just removes some of the loose debris, but those techniques are ineffective for stuck-on debris. Brushing with a wet brush, like a paintbrush, is pretty good. Some debris usually remains though. Ultrasonication removes most of the debris, but some is usually still stuck on, and that method can destroy some small and delicate structures, which I've seen happen. Scrubbing with a wet Kim wipe or soft cotton cloth removes most of the debris, but often leaves fibers on sharp edges, and it can sometimes scratch or damage some samples. Etching chemicals can be very effective, but they take a lot of time and effort to optimize their use, and they can sometimes react with the sample, which we definitely want to avoid. Okay, we've finally made it to the fun part of the presentation. Let's look at some applications of FIB, laser FIB. You've already seen Hugh's cross sections. This one is from the Zeiss laser workflow video. It's more than just a simple cross section though, so I'll come back to this example later. Here's a cross section through a 500 micron thick galvanized steel. It's about 400 microns wide, and the side gaps are about 200 microns at the top at least. Now I could have done a better job at improving the sidewall angles, but the phase boundary between the zinc at the top and the steel is clearly visible, as well as the steel microstructure quite well. This is the typical shape needed for a 3D FIB tomography acquisition setup. So from here, we would send this off to our PFIB to perform a tomography acquisition, perhaps also with 3D EBSD, which we also do here at CCEM. The laser processing itself for this was only a few minutes, and it will save many hours of milling on the PFIB to get to this point. I should mention that I spent some time testing to get to that quality level, but it's still not perfect, and perhaps a second time after this would have been even better. So this is far more than just 4 minutes of work, but subsequent preparations of a similar sample could take full advantage of previous efforts and immediately skip to doing it right the first time. One of the new things that laser FIB enables is accessing very deep into samples, far beyond what was practical to do with just FIB alone, and far faster than attempting to do it in a PFIB. However, once access is revealed, there are challenges to successfully use it for characterization. SEM imaging, that's easy, although not so much if the cut that you just did is in the middle of an insulator, because your conductive coating is no help down there. EDS analysis, that could work, but you need to be careful to avoid shadowing from the trench walls, and the best strategy here will depend on the position of the EDS detector in your chamber. EBSD has a line of sight that requires extreme angles, so that won't work for interior cross sections, but it could be fine if the cut is exposed all the way to the edge, and the sample is mounted near the edge of the stub, or ideally overhanging it. For 3D FIB tomography, well, the first challenge is that all the material above the target region of interest must be removed, and ideally at a perpendicular angle to the laser cross-section cut. Data can then be acquired from internal features if they're shallow enough to permit the deposition of essential protection and tracking deposits. But for deeper than a few tens of microns, it's not likely possible without an extraction. Deep features near an edge could be cleared out to right to the edge. That may enable acquisition. Deep internal features too far from an edge need a block lift out extraction or physical cutting to bring the edge closer so that you can then laser cut all the way. For a FIB extraction, the attachment point must be still fairly shallow, because manipulator access is an issue and GIS access to deep features is especially a limitation. For the more nano stuff like TEM, atom probe tomography, and the more nanoscale X-ray methods, the lift out is typically required. So that's feasible when attaching at a shallow depth, but again, deep lift outs are limited by micromanipulator and gas injection system nozzle access. There are a few ways to get around lift out limitations by making the sample become its own holder, for example, but more on that later. So in conclusion, one does not simply characterize deep sample features, despite that exposing them is now easy. I'll provide some visual examples of accessing depth. Here's an example from Zeiss of a cut to ROI method. Imagine if there is a buried region of interest somewhere deep down from a known surface position. The blue dot is the buried treasure here. With the laser, you can quickly cut trenches on the top and bottom to form a large lamella, like in standard fib preparation of TEM samples, except here it's about 20 times bigger. Then back into the SEM chamber, the top portion above the ROI can be removed by fib. Then the stage can be tilted to 54 degrees to do fib trenching and back to 0 tilt for the lift out. Right, well, here's their example. I think they may have stopped the test there because they didn't actually show the successful lift out. Some systems like mine have the micromanipulator at a shallow approach angle, and in this case, the tip may not actually be able to reach down there to the sample without hitting the sidewall at the original surface level, or it'd be very close at least. In this example, the cut to ROI was 75 microns down. If it was a bit deeper, like say 300 microns down, then this method will definitely not work, because even if a large trench is made for the manipulator to get access down there, it still won't work. Here's why. The lift out step has to be done at the coincidence height. But if the region of interest is 300 microns below the surface, then you bring that up, and at the coincidence, now the original surface level is 300 microns above the coincidence height. When you go to insert the GIS nozzle for the attachment deposit, it will crash into the original surface, and you're going to have a bad week. Now, it may be possible to also cut out a pit just for the GIS nozzle, but they're pretty big, and that's really an expert mode stunt. There are safer ways to do this TEM sample here. So let's try it again. Okay, we have some deep features that can be lined up from the surface level and prepare the laser trenches to expose two sides. Then instead of cutting to ROI right now, we hold off and instead prepare a fib undercut. Next, we could lift out the huge lamella and attach to a fib grid. This is quite feasible since the attachment was at surface level, not deep. Now, it takes a beefy deposit to lift out huge things like this, but it does work. Okay, now we do the cut to ROI and have no geometrical access problems here. Finally, we do deposit protection layers and then thin the windows for TEM. We get one sample targeting 3 different depth ranges, all in the same vicinity here. So one thing to note, handling this fib grid safely is now a bit of a concern, but because it's a weird shape, but I have a solution to this coming up very soon. I've made very similar sized lift outs to that one with laser fib from this cutting tool here. This is a ceramic composite of tungsten carbide particles in a cobalt matrix. We use this for EBSD, and I did a fib polish there, which added a few hours. The EBSD is enabled because we could sit this grid flat on an SEM stub at the edge, so no problem with the line of sight angles. I could have made TEM thin windows from this too, and that was the original plan, to follow EBSD at key locations with TEM, but we decided we didn't actually need it. But you can do it. There's a major difference here though from between this and the previous example, did you notice? This is no standard regulation fib grid. This fib grid was also made with the laser from a 350 micron thick silicon wafer. Now, it was my version 1.0, and I've since greatly improved the design and also acquired far better starting materials, but this worked okay. The grid is thick enough to handle easily with tweezers. You could peel it off carbon tape and copper tape. There's no risk of it bending. There's no risk of contacting the attached sample because it's a bit internal, unlike the previous example, precariously protruding from a standard fib grid. For fib tomography, accessing deep, well, instead of a lamella, you can lift out a block. You could also add an extra laser cut for the interior side trench while still having a tall section for a strong attachment to the grid, like I've shown. A block lift out, though, is a lot more milling than for the fib undercut than a narrow lamella. And being so thick, it's even more sketchy to use a standard fib grid. So it helps to have a thick fib grid that can keep the block protected within the grid walls. Also, it doesn't really have to be a 3mm semicircle shape if you're not doing TEM. So to do the tomography acquisitions far below the original surface level, the grid could be mounted horizontally after attachment, and then another laser step could be used to chop off the top to any depth, and then you can follow that with a fib cleanup to get a smooth top. And from there, it's just depositing the protection layer and tracking marks, and then tomography acquisition can begin. You may be wondering how, we target the regions of interest when they're hidden deep below the surface. Well, sometimes this can be informed by the researchers' experiments, or perhaps they want to explore what's happening some known distance, say 30 microns below the surface, or they know a specific feature from maybe a microelectronics schematic. But what if we don't know yet where the buried treasure is located and first need to find out? What, do we have X-ray vision? Actually, we do have X-ray vision. No, not you. We have 2 new X-ray microscopes. You can find out more about them on the CCM website and by contacting Pardis or our manager, Brian. But basically, the Zeiss X-Radia 630 Versa is really on the cutting edge of resolution and efficiency for its sample size range, which I think is typically a few millimeters. The Nikon M2 is for really big stuff, many centimeters long. The data from X-ray microscopes can tell us where to find the buried treasure so that we can access it with the laser fib. Considering sample sizes, usually the Versa will be the step prior to laser fib, but we could first take something big into the Nikon M2, roughly find a target there, physically cut out a smaller piece, then take that to the Versa for a higher resolution scan and go from there. Okay, do you remember the Zeiss laser fib workflow video? That pathway actually started at X-ray microscopy. Here's how it goes. This first step is optional, but prior to the X-ray microscope acquisition, it really helps to make sure that there are enough landmark features on the sample surface and that they're fine enough to enable precise targeting from the surface when the sample is in the SEM. The laser can easily do that marking, and I'll show you the details in the next slide. So the next step is to perform the X-ray microscope tomography acquisition. Then you process the data, identify the regions of interest to further analyze. This could be done in 2 steps also. First, you could do a quick whole sample X-ray overview scan, and then follow that with a high resolution X-ray scan at interesting locations. With target acquired, we move the sample to the laser fib. Next, the tomography data has to be imported into the Atlas V correlative workspace. Then we acquire an SEM image of the sample surface containing the surface markings that have been patterned in. And then in the Atlas workspace, we move and rotate the X-ray data to match up the top of the data set with the SEM image of the surface. So now, by doing that, we've linked the X-ray data to our live SEM positioning. We note the depth from the surface of the target ROI and map that location up to the surface level. Next, we register an SEM image of the target location and also send the stage positions of the laser holder, fiducial markings, to the laser mill software. Then we transfer the sample to the airlock for laser processing. Back to the SEM, we identify the target locations. Again, we could use the X-ray data and ALICE to help us pinpoint if it's not obvious from the cross-section. So with an understanding of the ROI location, we can then do a fib polish to clean up the cross-section and carefully approach the target. Once there, we acquire images and whatever other analysis is needed. Our X-ray microscopes, they're quite new, but we do have all the capabilities to do this kind of correlative workflow here. As promised, more details on the surface marking. So I received the sample of trabecular bone embedded within a resin block. With the laser, I marked in this navigational grid with a cell spacing of 200 microns across an area of 7 by 10 millimeters. This marking took the laser just 80 seconds to finish. Here's what it looks like in SEM and by light microscope. And yes, it's quite visible in the X-ray data too. So this grid marking enables easy and precise targeting, as well as better communication between everyone involved in the process. After a quick survey scan, for example, the bone researcher can look at the data and tell the XRM specialist, let's take a high-res scan from top left S20 to bottom right Z26. Then after checking in with that data, she can bring the sample to me and say, hey, I need an EDS map at a place 400 to 500 microns below the top right quadrant of X23. So surface markings are good, definitely worth the effort. In establishing these workflows from X-ray microscopy to the crossbeam laser fib, we can continue down the chain towards many of our other characterization tools. Some analysis can be done with the crossbeam itself. For large volume serial sectioning work, we can prepare samples for our plasma fib. We can also pick out small locations from X-ray data and prepare samples for atom probe tomography and the various TEM techniques on our many TEMs. So we're now set up to take a sample from the centimeter level, characterize at every length scale along the way, all the way down to atoms. And our laser fib really is the hub of all of that to get to all these endpoints. Moving on to another application, mechanical testing. It's really important to quantify the mechanical properties of materials, and it can be useful to do this across a variety of length scales. Traditional methods test bulk properties in the millimeter and centimeter range, and FIB has enabled the lower microscale range to be tested. And I've made some of those samples over the years, examples shown, but the range in between those, let's say 50 micron to 2 millimeter range, that's hard to test. It's too small for cutting tools, but too big for FIB. Well, in between those, that's where laser FIB lives. So there's a lot of mechanical testing to be done. And now that this range has become accessible, especially site-specific mechanical testing can be done too. So here's an example. A student has been bringing me metal foils of different materials and thicknesses ranging from about 50 to 200 microns. She needs arrays of microtensile samples from the edge of the foil with a specific standardized shape. Here's the schematic. How it works is the testing rig inserts a pin through the hole and then pulls the narrow gauge length and tension. So with the schematic, I drew it up in the CAD, except we need the laser to scan the space between the structures rather than the tensile specimens themselves. So it's a bit hard to draw or different. Anyway, here's what they look like. And an array like this takes a few minutes to process. The tensile samples are 400 microns wide and almost 1 millimeter long. And following the laser work, the student used FIB herself to thin the gauge length to a very narrow strip. This was partly site-specific because I had to place them on the edge of the sample, but also we can target specific grains or even specific grain boundaries that are near the edge. For another set, the student used FIB to write some fiducials into the metal surface and then gave me measurements for where to precisely position the center of the gauge length for these structures. So here's what that looks like in the LaserCAD software. I was targeting parallel to the milled line and a specific XY distance from the X. For scale, the X is about 20 microns wide, that fiducial X, and the gauge width is about 60 microns. So this is a moderately precise targeting within about 10 microns. Here's another mechanical example. Remember earlier I showed you this 500 micron long bent cantilever in 25 micron thick tungsten foil. He followed that, Manuel did, with FIB to make a notch to control the crack propagation site. Oh, and he made an array of 100 of these cantilevers in about 30 minutes. With femtosecond lasers, you can work in length scales that are large enough for samples to also be their own holder for other microscope techniques. Anaprobe tomography needles, needle sample prep, they're most commonly prepared by FIB, by lifting out and attaching small blocks of material to the top of a few cones that exist on a purchased microtip coupon array. That method is time consuming, so when we do it, we typically only make 4 to 6 atom probe samples at a time, although that's usually enough. In this example though, the researcher has a silicon wafer with a titanium nitride coating and uses femtosecond laser to turn the wafer into its own microtip array by ablating around the cylinders and leaving them intact. This array is 1.5 millimeters by 4.5 millimeters and ablated down to a depth of about 130 microns, taking 70 minutes using an average power of 50 milliwatts. Then FIB was used to sharpen the cylinders, of course, into atom probe tips. The location of the cylinders was not site-specific in this case, and that's not actually possible with their external laser system that was used. But with the crossbeam laser FIB, it would be possible to choose specific locations for the cones if you want. The next example, this is another sample as its own holder. This is for TEM. So thin samples, such as rolled sheet metal or wafers, can be cut into half circles. Here they have 300 micron thick copper, and they just likely used a punch or maybe ultrasonic disc cutter here to make the semicircle. However, it's certainly possible to cut a 3 millimeter diameter half grid shape from this material using femtosecond laser. You've seen one of my examples of it before. Although in this case here, since the shape isn't critical, then laser is maybe not the most efficient method. But with this piece, laser FIB was used to prepare the large lamella trenches on both sides. Then once down to a more practical thickness for FIB to work with, it's possible to cut the top to target a deeper region if you want, and then a TEM thin window can be prepared, or actually there's room for dozens of them if you want. With this example, researchers came to me needing a TEM sample prepared from the surface plane at the edge of a 500 micron thick lithium niobate chip that has electronic structures patterned on the front side. They want to use TEM to study the surface wave effects caused by the electronics, so this cannot be done by a lift out because then you wouldn't have the surface of the chip. So I made a large trapezoidal trench to clear out the entire thickness of the chip at an edge from the bottom almost all the way to the top. The trench is 470 microns tall, 115 microns at the top, and 255 microns at the base, and it's about 200 microns of depth that was removed in there. This laser process, as usual, was just a few minutes, despite that the material is a transparent insulator. I used fib for trenching to approach the surface and then to thin 2 TEM windows, which are 40 microns apart. They wanted a big space there, and they also wanted them to be different target thicknesses. I had to also remove about 25 microns from the edge since it was quite chipped. So there was a bit of cut to ROI kind of technique in here too. I've already shown a few things made by the laser that are big enough to hold in your hands, but there are a lot of possibilities for stuff like this. It's less for doing science and more about convenience and problem solving, and maybe a little bit of fun too. These are still useful things though that you can do with a laser. Certainly not the reason to buy a laser fib, but they're cool. In the membrane box here, I've custom made some 200 micron thick aluminum TEM spacer washers. I've also made some anti-twist washers. The TEM operators here wanted a specific spacer thickness that they didn't have, and it turns out that these things are expensive to buy, so I made a few. The other example shows a 25 millimeter aluminum SEM stub with a sheet of 200 micron thick aluminum mounted on top, but slightly elevated above the stub level. And with the laser, I've cut 40 slots that are 3 millimeter long by 200 microns wide to hold custom fib grids in a vertical orientation. The 10 grids in there at the top, they were also made by LaserFib. I'm not going to tell you what they're for because we think it's quite publishable, but haven't done that yet. But I just want to show you that there's a lot of opportunity for doing creative things with the laser that are big enough to actually see and touch, which is strange coming from the world of fib. You might think that transparent materials are not possible to laser ablate since the wavelength of laser light means the photons just pass right on through the band gap. Well, fortunately, it still works. It just requires a lot more optimization than, say, for metals. Sometimes I've found that some parameters barely put a dent into the surface of a transparent material, but then I make a few small changes and it makes all the difference. Burst mode is very helpful for working with this class of materials. The physics is based on nonlinear optical processes, such as multi-photons combining forces to excite individual electrons. Below is an example from Zeiss showing successful ablation through glass cover slip. And on the right are my own examples. I've already shown lithium niobate, but here are wafers of single crystal silicon carbide, both 4H and 6H types, and also sapphire, which is really hard, all being cut completely in half by the laser. Bigger pieces were 1 centimeter square cut into quarters, and the smaller pieces were 5 millimeters square cut in half. Okay, thanks for joining me here. I hope you feel well informed about LaserFib now. You can watch this fib presentation again on our YouTube channel in a few weeks when it gets uploaded, and we have many other webinars there. Thanks.
Thanks, Travis. A great presentation. I personally learned a lot about the laser and didn't realize that you could do quite as much with it. So there's some questions that came in. We'll go over them. So the first question apparently is a multi-parter. So I'll do it kind of one at a time. It's regarding the LIPSS. Are the lips found on both the cross section of the sample as well as the plane surface perpendicular to the beam?
Yeah, they can be. If you just do a few pulses and kind of like low fluence, then you'll see them on the perpendicular plane. But most of the time, if you're really blasting things, which we are, then the bottom is way too rough to even see the lips. You just have a bunch of spikes that are like multiple microns tall. So most of the time you'll only see them on cross sections where the laser processing gives a much flatter surface.
Okay. Okay, great. Can characteristics of lips like depth, periodicity be tailored by changing laser parameters, i.e. can the laser fib be used structures, surfaces on the nanoscale?
Yeah, I was going to make a slide about this, but I ran out of time. But yes, so while I would prefer to destroy the lips and never see them, there are some people who like them and want to adjust laser parameters to change the structure of the lips, change the height, change the angles, change the spacing. And yeah, you can do things with that. You could make, if they're really thick, you could make like hyper hydrophobic surfaces. And then the existence of those ripples tend to cause color effects. So if you have different parameters of ripples on a sample, you can actually have different colors being seen on like a metal surface. So there was an example, someone did like they made a painting using a wide variety of colors that they programmed in by tailoring the laser parameters. Yeah, and there are a few other things you can do with it too, but yeah, definitely playing with the laser parameters can manipulate the lips, but you can't really avoid them.
Great. And then two more questions. Do you do or plan to do APT sample preparation in the crossbeam using either laser fib or cryo conditions and cryo transfer to the crossbeam 350 to the CAMECA LEAP?
Yes. Yeah, we haven't done that yet because it's still fairly new, the cryo system, but we do have full capability of doing we can start from something like even a liquid and freeze it and then transfer that under vacuum and cold to the crossbeam, do fib things to it. We can even do cryo lift outs because we have a cryo gripper. And then so we could prepare atom probe samples. And then we have the cryo shuttle to transfer cold and under vacuum to the LEAP. So yeah, we bought those systems in order to do exactly that. And we have the capability of doing that. We just haven't quite had a request to do it yet. But yeah, we will, and we will practice it too.
Great, you
And
actually answered the second part of that question in your answer. And to follow up, we'll also be having a cryo APT webinar coming at the end of July. So I think that would probably be of interest for this person that answered that.
yeah, just one more for the second question. It's not just the VCT 500 shuttle that goes to the atom probe. We had to buy a special shuttle from Ferrovac to do this, and also special docking onto the LEAP. So it was a lot more complicated than simply just using the VCT.